After all, in the morning I was discussing about dimensional reduction technique called the principal compound analysis. So now let's see its application where we can use, especially in the processing. Okay. See, the goal is to represent the image in the space of lower dimensionality using PC. So our aim is, so using by reducing some dimensionality, I want to represent the image in a lower dimensional space. Okay, so this can be achieved with the help of the principal component analysis or any other technique. But the PC has some special applications as far as the image processing is concerned. Okay, we will see that. So useful for various applications like face recognition and image compression. So you can use this PCA for detecting of the face. That is a face recognition is different before the face detection. So once you detect the face, you have to face detection means so whether there is a face or not. Face recognition means whose face it is. That is a big problem. Then image compression. So once you know that, if you are able to represent the same image in a few number of dimensions, then our job is done, right? We can with those number of features we can store the information and we can communicate that into images and also that we can use it for the image compression also. Given image is of size n by n, so there is a images, our number of images are m and the size of each image is n cross n. Means the number of features in each and every image, the number of features because each pixel is a feature in the feature when you are processing the images. So the number of features will be n square. The number of features. So each and every image will have n square. The first represent each image as a 1D vector. So what is this 1D vector over here? If you see this is the 1D vector. If you see this is this is a one dimensional vector. The size is n square cross one column or 1 by n square, one row. If it's a column matrix, it is 1 square by 1. It's a row matrix, it is a 1 cross n square. So this is means what we are trying to do. So the image is converting like a 1D vector. This is called flattened vector. We are doing indirectly flattening of the image. This is nothing but flattened image. Right. So we are stacking the rows together. Okay. So now that the for face recognition, suppose what is happening when you are doing the flattening of image. So sometimes you may lose temporal features or spatial features which may relate to the position, illumination, and all this stuff. So sometimes when you during this flattening of the image, you will miss some important some features related to the position and all those tempos. That's the reason what we are trying to do. So we want to use if at all if I use it for the face recognition, whether the so face recognition is a next step of face detection. First, you have to detect the face, then you have to recognize the face. Okay, the note that for face recognition, faces must be centered and of the same size. So this is very important, like because always the faces has to be centrally located. If you look at in all the images, the faces. This is one of the limitation. If you want to use a PCA, for what purpose? For face detection. We will see and of same size and the faces must be centered and of same size. This is one limitation. The key challenge is the that the covariance matrix now is n square cross n square because suppose there is images and in all the images the face is at centrally located. Now I want to apply the PCA means you have to find the covariance matrix and the number of features will be square n square, number of features are n square. Then the dimension of the sigma x is number of features into number of features, nothing but n square into n square. So computing the covariance matrix for this problem, Is it difficult, right? Isn't it or not? Because in the earlier the size is 2 by 2 or 3 by 3, maybe 10 by 10, but a pixel which consisting of 250 colors, very small. Nowadays, the images are coming 1024 across 1024, more than this also. Okay, imagine if a image resolution, this is the number of features is equal to 1024 square, this is n, then it is n square into n square. So it means that so huge complexity is there to deal with sigma x, finding out the covariance. Right now, let's see how we effectively we can compute the covariance matrix sigma x of a when you are dealing with the images. The sigma x is the covariance between the each and every possible feature. So that is means summation of I is equal to 1 to m, the 1 to m, and phi into phi I transpose. You will get the phi I and phi I transpose, you will get the same. Where phi I is the transform data and phi I transpose is transposition. Okay. Now it's something like if I am writing it right, so 1 by m. So if I'm removing the summation, it is nothing but 1 by m a into a transpose. What is the a over here? The a is nothing but the concatenation of all the pi values. All the pi means the transform data values, alpha transform data value. So nothing but a is equal to the pi 1, the pi 2, and pi m number of features. Each feature number of features, and because the dimension of sigma is m cross m. In this case, the number of features are m, so it is m cross m. So that's it is m, and similar in this case also m. So in the phi into phi I transfer, this is phi 1, the phi 2, and then phi m. Now what we are trying to do now, the phi I, what is the dimensionality of the phi 8 A matrix now? Hmm? What is the dimension of the, what is the number of features over here? It is n square. Here it is m, so it is n square cross. Yeah. Now simple mathematics here. Now sigma x is now an n square n matrix and computationally expensive to compute its eigenvalues and eigenvectors. Obvious, right? Like eigenvectors means mu I, ui, and eigenvalues means lambda I. So what I'm trying to do that, so sigma x is nothing but sigma x into ui is equal to lambda I into ui. The sigma x I'm replacing to a into a transpose, where a is the concatenation of this. So A into A transpose. Now I simplify the formula into A into A transpose into Ui is equal to lambda I into Ui. So right, we will use a simple trick to get around this problem, by relating the eigenvalues and eigenvectors of A into A transpose to that of A transpose into A. So actually we are interested to find the eigenvalues and eigenvectors of A into N transpose, but there is a small trick. Suppose we can achieve this computation very easily by A transpose and A. We will see now what the logic behind before between A into A transpose and A transpose. Now let us consider a matrix A transpose into A instead of M by M matrix. So what you are trying to, you are considering a matrix A transpose A. The A transpose A is actually A transpose A. You are replacing in place of sigma x. The dimension of sigma x is m cross m, and this is also m cross m. Okay. Now suppose the eigenvalues and eigenvectors are mu I into vi. So this is the formula. So mu eigenvalues, this is an eigenvector, this is an eigenvalue. Values will be here, ui into vi. Now multiply both sides by a. So what I'm trying to, I want to apply the I want to apply a on the both sides. So then a into a transpose into a into vi is equal to a into mu I into vi. Now I can rearrange these terms as like a into a transpose into a into vi, mu I into a into vi. So A into Vi is equal to mu I into A into Vi. Assuming A into A transpose is equal to mu I is equal to lambda I into mu I. So in this case, what is the lambda I? The lambda I will be A into Vi. Lambda I is equal to A into Vi, and so lambda I is equal to Ui. So lambda I is equal to Ui, and what is the Ui? Ui is equal to A into Vi. So this will be Ui. This is Ui into lambda I. So what is the lambda I? This is the lambda I. No, don't forget that A is pi 1, pi 2, and pi. But do A into A transpose, A into A transpose and A transpose A have the same number of eigenvalues and vectors? Let us cross verify. So A into A transpose can have up to n square eigenvalues and eigenvector because its dimension is n square by n square. So A into A transpose can have up to n square eigenvalues and eigenvectors, but A transpose into A can have eigenvalues up to only m. So A transpose into A can have up to m eigenvalues and eigenvector, but A into A transpose I can have up to n square eigenvector. So it can be shown that m eigenvalues or eigenvectors of A transpose into A are also the m largest eigenvalues and eigenvectors of the A into A transpose. So even though the A into A transpose, E into A have n square eigenvalues or eigenvectors, but when you sort it, the topmost m eigenvectors are the eigenvalues of A transpose into A. Yes, our problem is solved, right? So we are interested in m eigenvectors, and now so those m eigenvectors are the eigenvectors, the k topmost eigenvectors in the A transpose into A. So now the step 3 of ECA need to be updated as follows. So what we are trying to do in the step 3, we are finding the sigma x, but now compute the A transpose into A transpose into A instead of A into A transpose, because A transpose into A transpose A have m eigenvectors. A transpose, if you find the A transpose, because the dimension is very simple, and A transpose A is m eigenvectors, and these eigenvectors are the topmost eigenvectors of the A transpose, A into A transpose also. Of course, we want the same, we want m eigenvectors. Those eigenvectors we can obtain from the A transpose into A instead of A into A transpose. The compute, because A into A transpose, the dimensionality is n square by n square. It's very used to compute. Okay, so compute A transpose into A, that is instead of A into A transpose. The compute mu and vi of lambda and eigenvector of A transpose into A. Compute lambda I is eigenvalue and mu I of lambda eigenvector are of A into A transpose using the lambda I is equal to mu I, and mu I is equal to A into Vi, then normalize Vi to the unit length. So what we are trying to do, so the compute the lambda and mu I of the A into A transpose. Once you know the lambda and mu I of the A into A transpose, then using lambda is equal to Vi and mu I is equal to A into Vi. So A into Vi will be the eigenvector of A into A transpose into A. So A transpose into A. This. The dimensional reduction step approximating x using only the first k eigenvectors as k less than m. So what are the k? We can use that trick to come up with the solution. Now let's see how we can. So what we did. So but in image processing area, so it is very difficult to calculate A into A transpose, because in A into A transpose, the dimensionality is n square cross n square. A into A transpose. So to deal with, we can compare with the A transpose into A. So that is the idea. So A transpose into A, you can get the m eigenvectors, and those eigenvectors is the k topmost eigenvectors of the A into A transpose. That's a clever trick. So instead of A into A transpose, so I am preferring A. We will prefer A transpose into A and get it solved, and you will get the eigenvectors, and the k topmost eigenvectors are the k topmost eigenvectors of A into A transpose also. A transpose into A. Now, so the step 3 to 5 of the PCA need to be updated as follows. What we are trying to, so this already did. Now let's see. So what is this data set? If you look at this data set, so in this data set, all the phases are centered at the middle. So all the phases are centered at the middle, and so then we get eigenphase or what is called a mean phase. So once you get the during the normalization process, what we are finding the mean of all the vectors. It's a vice versa. A vector can be represented as a image and vice versa. So once you have a new vector, this is the equivalent image is represented as mean phase. The equivalent phase, the corresponding phase as a mean phase. How can we visualize the eigenvectors and of an image? Their values must be first mapped to the integer values in the interval 0 to 255. First, you have to do some kind of pre-processing and normalization steps. In that, you have to look at all the values and that must be mapped to the 0 to 255. So for f min and f max are the minimum and maximum values of the given eigenphase, and that could be negative also. So where f min is the maximum value, f min is the minimum value of your eigenphase, f max is the eigenvalue, maximum value of your what is called eigenphase. So if x belongs to f min and f max is the original value, then the new value y is equal to y belongs to 0 to 55 can be computed as follows. This is a kind of normalization process, so we are followed there. So we are reducing the space. Now, how can I interpret this? How can I represent a phase in terms of eigenphase? So this is my actual phase. So this is my actual phase. This is my actual phase. This phase is represented with the help of other phases V1, U2, and U3. Represent a phase in terms of eigenphases. So the V1 is nothing but the face of this guy, V2 is nothing but face of this guy, and Vn is nothing but the face of the kth guy. So means so once we get the data and we can analyze, I mean, we can get back its image, and from image we can get the data. So once you get the data, you are once you get the data, to get the data wise. So this image data, so this image has to be represented in the form of eigenfaces. So y1, y2, they are all eigenfaces. Now, how can we use this what is called PCA for the face recognition or object detection? Okay, the simplest approach is to think of it's a template matching problem. So how there's a particular template. So how we are matching this template with the respect to existing templates. The problems arise when performing recognition in high dimensional space. When so same problem algorithm is applied for the high dimensional space, it won't work well. So that's why we required some kind of a reduction technique to trim the dimensions of your data. So face recognition using eigenfaces. So process the image database. So what is you have to process the image database. Process the image database, that is set up images with labels typically referred as a training data set or training phase. The compute PCA space using image database, that is training data. Represent each image in the database with k coefficients. K coefficient means so when you are transforming from the k dimensional space, you have to represent the image with respect to those dimensions. So that's why a image must be represented with the k coefficients. So given an unknown phase x and what we have to perform, given unknown phase x, so subtract the mean value and project unknown phase in the eigenspace. What we are trying to, we are projecting in the eigenphase, and from the eigenphases, so the closest match can be found. So once we find the closest match, how the closest match is found? By using sorry. So given an unknown phase, then what are the things we have to carry out in order to detect the phase? Okay, whether it's a phase is available or not, whether it's a phase or not. Okay. So what we are trying to do, we are subtract the mean phase. So we are already calculated the mean phase. The already shown how the from because once you represented in the form of vector, so you can reconstruct the image also, the corresponding image. So once you get the mean, you indirectly subtract like PCA steps only. Subtracting the mean means to make the zero mean data means you have to subtract the mean phase from your actual phase. So then you will get 5. The project unknown phase in the eigenspace. What we are trying to do, we are projecting this phase in the eigenspace. Eigenspace in the space. So there are k eigenvalues. So this is there are how many eigenvalues will be there? Because there are n dimensions, so that many eigenfaces will be there. So that means there are k eigenfaces will be there. So what does it mean? The projecting the unknown phase in the eigenspace means you are representing this unknown phase in terms of k eigenfaces. Okay, one eigenphase 1, eigenphase 2, and eigenphase k with some coefficient C1, C2, and Ck. Like this. This unknown phase is represented. This is nothing but a projecting into the unknown phase. So now you have established an unknown phase in terms of the eigenphase. To get this eigenphase, so so what now the database is also stored in the form of eigenphases. The database, all the images in the database is also stored like this. Same way how so every image is converted represented in the form of eigenphase. Now we can find the closest match. How we can find the closest match? The find the equivalent distance. The find the closest match sigma from training data set using the equivalent distance or Mahalanobis distance, isn't it? The important thing over here is the process the image database set of images with the labels. This entire training database is mapped in converted into each and every image in this database is represented in the form of what is called eigenfaces. So now because we are converting unknown face also eigenfaces, so we can for the comparison purpose it is very easy. Now the closest match can be found by using the calculating the other equivalent or Mahalanobis distance between these two images. Okay, recognize X as a person K, where the K is the ID linked to the sigma. So recognize X as a person K. So then where the K is the ID linked to the sigma. So the corresponding ID will be. So for intruder, let's see how it is. We can use the for face detection and recognize. So first you will detect the face. First you will detect the face, and then you will identify the whose face it is. Now, how so far we have seen how we can use it for the face recognition. Now, our idea is to use it for the face recognition. Now, how we can use it for the face detection? Okay, so given an unknown image X follows these steps: subtract mean face X bar and project unknown face into the eigenface, a common, and compute the distance. ED is called the distance from the face space, and if this is below certain threshold, if the ED the distance is below certain, then X is a phase. X is a phase, but whose phase it is, then you have to do this process. Like almost the same. This only the step 4 will differ. Recognize X as a person K, where K is the ID linked to the sigma high. So whose based on this K value, we can identify the which person it is. Okay. Now for the face detection, so we are putting some threshold, and then X will be qualified as a face. Once you detect this, you can apply the face, what is called face recognition. So now how we can represent an image in the form of the eigenfaces, and once you are eigenvectors or eigenface. Now in the earlier we called eigenvector, now in the image, now vector is nothing but image over here, that's why it is called eigenfaces. Now we can, of course, when you have eigenfaces, and from the eigenfaces you can reconstruct the image too. Okay, now the reconstructed image looks like a face. Okay, so from this is a eigenface. From this set of eigenfaces you are reconstructed the the original image. Okay. So eigenfaces. So with the help of the eigenface, the idea of how we can use the PCA for the both face detection and face recognition is we can with the we can represent each and every image as a eigenfaces, and so we are finding the closest match between the eigenfaces. If this match is below certain threshold, you can detect the face, and based on the, or if you are this based on the key value, so you can identify the whose person it is. Okay, so it can be used for the face detection and face. Once you detect the face, you can track and recognition too. Okay. So what are the certain limitations of this PCA? So we are seeing that the PCA is very good for the what is called detecting of the faces and recognition of the faces. But what are the certain limitations of this PCA, principal component analysis? The background changes cause problem. Means if there is a change in the background, so definitely we can, a PCA is not effective for the face detection and recognition. So de-emphasize the outside of the face, for example, by multiplying input image by a 2D Gaussian window and centered on the face. So it means if the background is highlighted when compared to the your face, then we cannot use this PCA for face detection and face recognition. So light changes when there's illumination changes, so that will also affect your performance on the detection of and recognition capability of using PCA. So performance decreases quickly with the changes to the face size. So the performance is totally depending on the size of the face we are dealing with. So what size should be there, and that should be centered in the middle. The performance decreases with the change in the face orientation. Also, if there is change in the orientation, then the piece is also cannot be suggestible for using face detection, and it is called face identity. That's why people have used the different models called deep neural vector. In the DL, in the CNNs, they will automatically extract all the features. You need not to do this process, okay? But because the CNNs are started using maybe in the 2016 or 17, but people this PCA was there since long time. The people have used this for the very early stage. They have used for face detection and recognition, but to extract the best features nowadays people are using, especially for image data, they are using computation CNNs, convolution neural networks. Okay. So the PCA is not always an optimal dimensional reduction technique for classification purposes. So we cannot, so PCA, especially for images, as I mentioned, there are some of the limitations of it when you are dealing with images, is not suggestible. So that's the reason people are using another technique is called LDA, linear discriminant analysis. If you look at here, so it is X1 and X2. So when I am projecting, this is a one principal component, this is another principal component. So when I'm projecting my data on this direction, what is happening? So there is overlap. So there is overlap. So there is some data points which are overlapping each other. Suppose if you see when I'm projecting a data in this direction, so means that there is no data overlapping here, and so there is a clear distinction boundary between these two classes. So when you are projecting in this direction, the expression next to direction, so the data is easily distinguishable. Hence, use it for the we can easily classify the sample. So when you are if any new sample comes, if it is in this region, we can say it is some positive class, negative class, and if it is in this one, we can say it's a positive or negative class, like that. So based on this, we can easily identify the class of the unknown sample because of the clear distinction between these boundaries. So this is called class discriminator information. So in what can we discriminate the two classes easily or not? So that is called class discriminatory information. So based on this, we can easily identify so the unknown sample class because of this clear distinction boundary. So that's the people that LDA will follow the same idea. So in the linear discriminant analysis process, so they will project the data in one of the direction in which the class discrimination is possible very clearly. Means even though the number of dimensions are few, even though it has few number of dimensions in the reduced space, but when you convert into the when you project into the new dimensional space, so the data should be is kind of linearly separable or separable something. That means we can easily the distinguish two class information by drawing a boundary. So that's why we can say the LDA works on the principles of the linear class discriminatory information. It takes into the consideration of the scatterness or the variance within the classes and between the classes. So, in which direction it has to project the data. So in which direction we should project the data is decided by the scatterness or the what is called scatterness between the classes or within the classes. So means scatterness is nothing but the compactness or variance of the data variance. How the data variance is there inside the class and outside the classes between the classes. So if you look at when I'm projecting the data, so this is the data, my whole data. When I'm projecting onto this in this direction, so what is happening? So there is some sample data sample which are already overlapped. Some sample which are overlapped. So if unknown sample come, we cannot make any decision about it, right? So that's why we can say bad separable data. If you look at the same data sample, when I'm projecting in this direction, it means that all the blue dots are in one side and all the red dots are on one side. So there exists a clear boundary. So if a new sample come by projecting onto this particular direction, I can easily distinguish that which class it belongs to. Okay, so this is a very useful, and of course, how we will decide in which direction you have to project your data is based on the scatterness between the classes and within the classes. Now let us study about the LDA, linear discriminant analysis. And some of the library functions LDA is also classified because it is it is project the data so that we can easily classify the data. Hence, we can also use LDA as a classifier, one of the classifier. Right. So now let's study something about this linear discriminant analysis. Okay, so let us assume that there are C classes with each class containing mi sample. So there are C classes and each class will containing the number of samples as mi, and so the total number of samples nb is the summation of all these samples in the each and every class, all the samples which are, so that's why m is equal to summation over I is equal to 1 to C, where C is the number of classes and mi is the number of samples in each and every class. Right. So M1 is the number of classes in number of samples in the first class. M2 is the number of samples in the second class. M3 is the number of classes in third class, something like. Now, once we have the total count, I mean total number of samples, let mi be the mean of the ith class. So what is the mean of? So each and every class will have their individual mean, like mu I, mu one, mu two, mu three, and where this mu I stands for the mean of the ith class, and mu is the mean of the whole data sets. Okay, so from the individual means, we are calculating the mean of the whole data set by 1 by C into summation of I is equal to 1 by C to mu I. So where mu I is the mean of each individual class, and where there are C such classes, and its average will be 1 by C. Now, how do we calculate within this class scatter matrix? Means the scatterness between between the clusters. Okay, this is called scatterness between the clusters, and this is the scatterness between the clusters. So if you want to find the scatterness within the cluster, so we have to it's a matrix. So it's a matrix. That matrix is called SW. The scatterness of within the cluster. How we are calculating the scatterness within the W is the summation of I is equal to 1C. There are C number of classes where mi is the number of sample, and x1j minus mu I and xij minus mu I transpose. So this is what is this variance? The variance, and there are C classes. Now what could be the dimensionality of this? What could be the dimensionality of this? Is it C cross A or something else? What is the dimensionality of this? What is the dimension of SW? By looking at this summation, can you guess what could be the? So for every sample you are finding this value, and then you are finding the covariance. Okay, where you are finding the covariance between this. Once you are finding the covariance, then how many times you are doing it for C classes means it's a C cross C. The dimensions of the series is C cross C. So the scatter is within the what is called within the scatter within the class scatterness is C cross C. Now the between the class scatterness, how much is the scatterness between the any two the classes? Okay, this is very useful because that will identify the best what is called discriminated information so that we can easily discriminate the data. So it is summation of I is equal to 1c and mu I minus mu into mu I minus mu, where mu I is the mean of the individual class and where mu is the whole data and mu I is between the class, how much it is, get a C class. Now, suppose the desired projection transformation is, so this is denoted as SB. So we have within the class and between the class scatterness. Suppose the desired projection transformation is means we want to transform so x to the y. We want to transform x to the y and that you have to multiply the x with the u transpose. Instead of t, we are calling u transpose. What is this u transpose? So what is this u transpose? You have to multiply with x so that you will transform to the y. Now suppose the scatter matrices of the projected data y are is SB tilde and SW tilde. Suppose there are two scatter matrices of the projected data are SB tilde and SW tilde. So means from higher dimensions to the lower dimensions you are projecting the data and the scatter matrices of the projected data means once you are projecting from here to then it is called SB tilde and SW tilde. Now LDS seeks transformations that maximizes between the class scatter and minimize within the class scatter. So when you are transforming the data from here to here, so what is the SBW and what is the SW? So we want to maximize this both SBW and we can maximize the between the class cluster. So between this class between this class scatter means so this it should be we are trying to maximize. They are pulling each outside each other, so this distance will be maximized, and within this it should be within the class it should be the maximized. The scatterness within the class should be the minimized. Okay, so overall we should be maximize this. Overall we should maximize the SB tilde by SW tilde. So between the class you have to maximize and SB tilde you have to minimize. Overall you have to the maximize or you can reverse or you can maximize nothing but u transpose and so what you're doing is the both the upper and lower you are multiplied with u transpose and your u transpose the left side and the right side you are multiplied with u and u. Now let's see how we can turns into. Now it can be shown that the columns of the matrix U are the eigenvectors. What is these columns of the U? Similar to that, it is the eigenvectors are called Fisher faces. Okay, Fishers. That's why it is called. LD is also called Fisherman linear discriminant analysis, and now if you look at here, so we are trying to maximize same SB tilde and this is simple SB and this is simple SW. These are SB tilde after transform. This is SW tilde after the transform. So this is about transform data before after transformation and this is before transformation. In original space, this is in the transformed space. Now, so it can be shown that the columns of the matrix U. What are the columns of the matrix U? What is this U? The columns of the matrix U are the eigenvectors. So those eigenvectors are nothing but eigenfaces. And they correspond to the largest eigenvalues of the following generalized eigenproblem. So where in the earlier case we have summation of sigma x minus lambda I is equal to 0. This characteristic we have solved to get what is called lambda values, but here you have to solve this characteristic equation to solve the lambda values. What is this? SB into the scatterness between the clusters between the classes is should multiply into mu k. Mu k is equal to lambda k into SW, where SW is within the class scatterness. This has to multiply with the mu k. In that case, so what is the lambda value you have to multiply so that both will be equal. Those lambda y is called eigenvalues. It can be shown that SB has at most a rank C minus 1. Therefore, the maximum number of eigenvector with non-zero eigenvalues is C minus 1. So, the if you observe the SB, the scatterness between the clusters whose dimension is C cross C, it has the rank of the matrix, and whose rank is maximum is C minus 1. So we in the theoretical it is already proved that the maximum rank of the SB is C minus 1. What is the maximum rank? Will say it is in a the maximum rank will denote the maximum size of the square matrix whose det is positive. It's not zero. It is not a singular. Which is not a singular. Okay, therefore the maximum number of eigenvectors with non-zero eigenvalues. That's why the non-zero eigenvalues is C minus 1. So so if you solve that particular matrix, then you will get C minus 1 eigenvectors. Means these C minus 1 eigenvectors are non-zero. Now, the another interesting thing is from this what we can infer that. So, what is the maximum dimension of LDA subspace is C minus 1 means if you know that is the number of classes and we know the output dimensions. So, what is the number of dimension? So, the output dimensions is fixed, that is nothing but C minus 1. So, from irrespective of your input, suppose even though it is 10 dimensions, it is having two classes, it means that so the output dimensions will have only C minus 1 only. The one dimensions will be there in one. The output the dimensional of the output is only C minus 1. That's the beauty, right? When C is equal to, we always end up with the one LDA feature, no matter what the original number of features was. Okay, irrespective of number of features, then irrespective number of features, the number of output features after performing LDA is 1. It is C minus 1. Now let's see, let us put together the PCA and A for the two-dimensional data. So this is two-dimensional data. So x1 and x2 and the C is equal to number of classes 2 and blue and white. Now blue and red. For the PCA there are two principles. The two-dimensional data, that's why there are two principal axes. This is one principal axis, this is another principal axis. But for the LDA you will have only this line. For LDA you have only one line because the C is equal to the number of axis in the new dimensional space is equal to C minus 1, that is 2 minus 1 is equal to 1. And here you can understand the why the LDA is lined in this direction. So because in this direction, so when I am projecting the data in the principal axis direction, in the first PCA axis, so what will happen? The data there is some overlap in this particular portion. We cannot distinguish it. But when the projection on the first LDA axis, we can easily distinguish that. So this data is belongs to one class. This data is belongs to another class. Now, if SW is non-singular, so means if the scatterness within the cluster, within the class is non-singular, we can also solve a conventional eigenvalue problem as, so if this SW is not singular, is non-singular, which whose data is not zero, then we can convert this problem as when you're bringing down this SW this side, we can SW inverse. Because it's a non-singular, so inverse is possible. Inverse is possible. Now this is converted into SB inverse into SW inverse into SB into UK is equal to lambda k into mu k. In practice, SW is singular due to the high dimension of the data because the SW is scatterness within the data, and so the most of the time the SW is singular due to the high dimensionality of the data, and especially in the image data sets and a much lower number of data. So when the data is high, the number of dimensions is more and the number of samples are less. In both the cases, there is a high chance that the SW will be singular. So to elevate this problem, so PCA could be applied for. So what we can do, so whenever there is a chance that when SW is singular, so because SW is singular, we cannot solve this characteristic equation. SW inverse is only solved when it is a singular, when it is a non-singular, but it is a singular when its det is zero, then how can we overcome this problem? So for that you have to apply, you have to make use of the principal component analysis. First you have to apply the PCA, then followed by LDA. First apply the PCA to reduce the data dimensionality, So then apply LDA to find the most discriminate directions. Okay. So then you will find so from X to Y and Y to Z. So that is the way we can make use of both PCA and LDA in image processing area. So so let us have some 10 minutes break, then we will resume our session. That is another feature selection technique and this. So with this, I'm stopping LDA. Then after the resuming session, we will discuss some more concepts.